Okay, so welcome everyone to our ECCV workshop on sensing, understanding, and synthesizing humans. So this is our actually first workshop on this topic. And in today's workshop, our workshop is in half day. We will have two invited speakers, Dr. Xinlei Chen and Prof. Siyu Tang. And we also have 3 challenge sessions on the PointCloud-C challenge. So there's more on this robustness of 3D perception, and as well as this OmniBenchmark challenge. So this for the 2D perception for the generalization. We also have this PSD challenge for the Panoptic scene graph. So this schedule of our today's workshop. We'll first have our first speaker, and then 2 challenges, then the second speaker, and finally is our third challenge. So before we go into the actual distinguished speakers, I would like to share some of the trends we have observed on the topic of sensing, understanding, and synthesizing humans. The first is kind of a holistic view on the integral pipeline of human sensing, understanding, and synthesize. So in the past 1 or 2 years, I think everyone has seen the success of like either text to image and image to text. So that is our human sensing and synthesize. They're kind of forming a loop, trying to reinforce each other. So that is definitely a very important trend for us to note. And I think our speakers also are sharing their works on how to learn better representations from the human's viewpoint. And the second trend is we're going from 2D to 3D, right? So our visual world is inherently 3D. And if we just solve the problem from 2D, there's a lot of ambiguity there. So a lot of like works either from the recognition discriminating model to this synthesized general models are on this from 2D going to 2.5D and finally go to the 3D side. So that is also another point, and our speakers and our challenges will also reflect this line of research. And finally is going from this passive vision to this active vision actually. This is active vision. We are not going just to let our agents sit and see. We are going to let our agent to move around and to interact with the environment, right? There's now a lot of works using large operation models to facilitate this kind of first-person view or this reinforcement learning, that sort of task. So that is kind of another move for our field. Okay, so that is very brief opening remarks from me, and I will give time to Ziqi.
Thank you, Ziwei. I am Ziqi Huang, a PhD student at MM Lab NTU. Today, our first speaker is Dr. Xinlei Chen. Hi, Xinlei. Xinlei, can you hear us? I think Xinlei has already entered the meeting room.
Yeah, I think Xinlei is muted. Yeah.
Hi, Xinlei. Are you able to hear us? Okay, I will just go and introduce Xinlei first. So Xinlei is a research scientist in FAIR AI Labs at Meta AI. His current research interest is on pre-training, especially pre-training of visual representations with self-supervision or multimodality. You might have heard of exciting works from Xinlei and his team, such as MoCo V2, MoCo V3, SynSend, and Masked Autoencoder. Today, Xinlei will talk about task-centric pre-training of visual representations. It's our great pleasure to have Xinlei here today. Xinlei, hi. Yeah.
Yes. Oh, can you hear me now?
Yes, I can hear you now.
Oh, okay. Okay. So it's good. Let me still try to.
Yeah, you can try share your screens, see if that works.
Okay. You can still hear me, right?
I can. Yes, I can hear you.
Okay. Good. Let me share the screen. And you can see the screen.
I can see you started screen sharing. Yes, I can see your slides now.
Okay.
Okay. Yeah, now it's full screen already.
Oh, okay, good.
Okay, sure. Okay.
Yes. Yeah, thanks for the invitation. I'm happy to be here. Sorry for the glitch of my microphone. Yeah, so just a more detailed introduction of myself. I have worked on quite a few topics in computer vision research. So during my PhD and during my time here at the fair as a research scientist, have worked on various topics. And most recently, me and my team, we have worked on self-supervised learning. And well, this is probably not important. The important thing I want to mention and to hope you guys can keep in mind during my talk is that I have actually never worked on human-centric tasks. So be it human understanding or human synthesizing or human sensing, I have not worked on any of these topics. So if I make any mistakes or wrong statements about human-related topics, please forgive me. So then, why do I think this talk may still be interesting to you guys? So as I said, recently, we've been working on self-supervised learning. And actually, self-supervised learning is all about pre-training representations. So it's a form of unsupervised pre-training or unsupervised learning. And it's unsupervised because it doesn't have access to human annotated labels. So what we will do is get the representations pre-trained from the task, pre-trained from the pre-training task, and then transfer it to downstream tasks like image classification, like object detection and segmentation. And of course, we can transfer it to human understanding. So that's where the potential relationship is. So to recap, unsupervised pre-training is all about learning representations that are useful for downstream tasks. So it doesn't matter how well we perform during the unsupervised or self-supervised learning stage by itself. So there are two popular self-supervised pre-training paradigms in the literature. So one, I will call it contrastive learning or Siamese learning, and the other, I will call it masked autoencoding. I'm not going to talk about the details of these two paradigms. And in fact, we have a tutorial tomorrow talking all about the self-supervised representation learning in computer vision. So you're welcome to join us either in person or remotely. But both contrastive or Siamese learning and masked autoencoding can help various downstream computer vision tasks in general. So these are very useful pre-training paradigms. So then why are we talking about task-centric pre-training if they are not general, because they are task-specific ones? Well, ideally, we want a better pre-training scheme to help all the tasks. However, real-world tasks usually come with different levels of importance and priorities. So for example, if some people may say humans are the measures of all things, so it's super important to understand human activities, and others may don't agree. So they think object detection is probably more important research for self-driving cars, for example. And the second reason is that tasks can have inherent conflicts with each other. So a classical example is classification versus localization. So for classification model to work well, it needs to model some kind of invariance, maybe in relation to geometric transformations like scaling, translation. But for localization task, in order to have a accurate or precise localization of some objects, equivariances may be more important, so that it can preserve the geometric transformations to the input. So you cannot do well on both tasks. And the third reason is that it's of course of scientific interest to understand which design during pre-training can help which set of tasks. And who knows that the next design we explore can be a breakthrough for the next generation techniques. So in this talk, I'm going to cover our recent work on task-centric pre-training. And specifically, our task of interest is object detection and segmentation. I'm going to talk about the two things. The first is point-level region contrast. It's built on Siamese or contrastive learning. And the second, I'm going to talk about long sequence masked autoencoders. So that's a recent work built on MAE, masked autoencoding. So the first talk is point-level region contrast. And this is an intern project led by Yutong, and I'm one of the co-mentors together with Alex Krylov and Alex Berg. So just to give you a brief background of what contrastive and Siamese learning is, given an image, we will create some view of the image, for example, by augmentation or cropping. And then this will be fed into an encoder to generate some representation. It's basically a vector. And then we will crop another view from the same image and feed into the same encoder with a different augmentation. And it will generate another vector, and the two vectors will form positive pairs. And we can, of course, generate representations from other images as well. And because it's from other images, they form as a negative pairs. And the term contrastive means that we will attract positive pairs and dispel negative pairs, so that the representations from the same image will be more similar to each other. And representations from different images will be different. And this is a Siamese learning because we are using and reusing the encoders with some weight sharing techniques. So it's just parallel encoders being used. And one important thing to remember is that we will represent each image or each view of the image as a single vector in standard contrastive or Siamese learning. But intuitively, it actually does not make too much sense because if we use one vector for all views of an image, it can be problematic. So here I'm showing an image. It contains a lot of objects. It's very crowded, seen from the image. But in contrastive learning, we will map all crops from this image to a vector, and we require all crops of this image to generate the same vector. So this means that it will be invariant to all kinds of crops and views, but intuitively, because a vector, it doesn't even have a spatial structure. It can be not so great for downstream tasks like object detection, segmentation, or maybe human pose understandings. And interestingly, contrastive learning is one of the most successful paradigms for self-supervised learning. And its success is reflected in particular on classification. So here I'm showing a figure. So this is from a recent work from DeepMind. And in the figure, there are two curves. Showing ImageNet top 1 classification accuracy as a vertical axis. So there are two curves. The bottom curve is showing supervised learning results with ResNet backbones, and they increase the size of the backbone from left to right. And on the top, there's a blue curve. This is a self-supervised learning curve. It's getting better results, like better accuracy than vanilla self-supervised learning. But more impressively, the self-supervised learning after pre-training, it's just doing linear probing on the top. So it means that after pre-training, the entire backbone is frozen, and we only randomly initialize a layer on the top, a linear layer on the top for classification. And on the other hand, supervised learning, it's end-to-end learning. So you can see that the power of self-supervised learning is pretty impressive. That after pre-training, we only need one layer, and it can already perform really well on the classification task. So this is there is a little bit of conflict here because for contrastive learning, intuitively it's mapping all crops from the same image to a one vector. It's a bit flawed, at least. But on the other hand, it's empirically achieving very good results, especially on classification. So this is actually very understandable from a task-centric perspective. So standard contrastive learning suits classification very well because it always represents at an image level, so one vector per view. And we will also do contrastive learning at the image level. So in fact, this is a task called instance discrimination. So treating each image as one class. And do classification on the number of images. The number of classes is equal to the number of images in the data set. And because it's contrasting at the image level, it doesn't care about locations inside an image at all. And on the other hand, object detection and segmentation are very different tasks. Usually, the benchmark will have multiple objects occur in the same image, and a single vector is usually not enough to capture all the information, especially the spatial information over there. And the task itself is also highly sensitive to locations. So I would say at least localization is equally important as a recognition or classification. So in this work, the point level region contrast work, we focus on designs that will lead us toward detection-centric pre-training. So we actually borrowed two ideas from the literature. So the first idea is to contrast at the region level. So the idea is to divide the image into multiple regions and then treat each as separate classes. So for example, showing here, we divide each image into 4 grids, and we require representations from the same region to be similar and different regions to be different. And then you can see that regions can be suboptimal because we don't have access to human annotations in self-supervised learning. The regions can be arbitrary. So in this case, it's dividing the dog into 4 parts. It's not ideal. Another idea, also from the literature, is that we can actually operate at the point or pixel level. So here we can actually randomly sample points or uniformly sample points from an image and do contrastive learning on top of that. So the advantage of this idea is that it's superb for precise localizations. So it's different from the previous region level contrastive learning. Here, the precision of a localization is only limited by the input resolutions. However, points alone maybe too much. It's too delicate for object recognition. So we believe some notion of regions are still necessary. So, for example, now we are dividing the image of the dog into 16 parts. It's probably not necessary to divide an image into so many parts. So at the high level, we try to get the best of 2 worlds in our point level region contrast work. Here are the illustrations. So we will divide the image into, for example, 4 regions. And then we will sample points from each of the region. And then points from the same region will get similar representations, and points from different regions, we will dispel them and make them dissimilar. And such a design is actually also making sense from the perspective of object detection. Because for detection, there are 2 very important aspects: recognition, basically classification of object categories, and localization, try to find where the object is. Our region level contrast is corresponding to recognition because it divides the image into regions, and point level operation is corresponding to localization, hopefully for more precise object locations. And in fact, when we have both point level operation and region level contrast, we can actually improve the regions as the training proceeds. So that's one of the best part of this model. So I'm not going to talk about the details, but at a high level, because regions can be defined by affinities between point pairs. So for example, the 4 grid regions here, it can be defined as, like, if we sample 2 red points from the upper left region, their similarity is 1. And if we sample a point pair from the upper left one and the bottom left one, their similarity or affinity is 0. So regions can actually be defined in this way. And in Siamese learning, it can be viewed as a kind of knowledge distillation because it has multiple weight sharing encoders. And one of the encoder can be viewed as a teacher, the other encoder being viewed as a student. So we can actually feed the points into the teacher network and get their similarity and use it to supervise the learning of the student. So point affinity distillation is actually like bootstrapping the similarities as a training goes. So here are some visualization of the learned regions and affinities. what we do is, given an image, we will also randomly sample a point, and then we will compute the similarities of all the features to the feature from that point, and then show it here. We compared 3 methods. So one is image level contrast deep learning, just treating each image as its own class. One is region level contrast, treating each region as a class. And then our point level region contrast. So you can see that for image level contrast, it's only looking at very local areas around the point. For region level contrast, it's better, but our point level region contrast is showing better similarities or affinities. And here are more visualizations from the paper. I'm not going to list all of them one by one, but overall, we see that point level region contrast shows very crisp boundaries around the objects, like humans here. And if we sample points from the background, so for example, this is very close to the person, but it's part of the background, the similarity will actually cover the vicinity of the person, but it's actually the background. It's kind of fun to check what the algorithm has learned. And of course, we have failure cases. So one failure mode is under segmentation. So given a point, it will also include pixels from other objects into the segmentation. The other is over segmentation. So in this case, only part of the object is considered within the same group. So the second work I'm going to cover is our very recent exploration of long sequence masked autoencoders. This is joint work with all the 4 times at FAIR, led by Ronghang and Shobik and Siding are helping on the project. In fact, we have already released the code. So if you guys are interested, you can play with it. So one improvement about this code is that we have enabled TPU support there. So you can run the original MAE code both on the TPUs and the GPUs. So a brief background about masked autoencoders. So at the high level, it's just given parts of the data, we want to complete the data by predicting the rest. And this idea is actually not new at all. But it was first made to work by folks from NLP. So they have this specific term called masked language modeling. And the idea is that they represent the sequence of represent each sentence or a paragraph by a sequence of tokens, and they will randomly replace parts of the token sequence by some masked token, or replace it by some other tokens from other sequences, and then try to reconstruct the original sequence of the tokens. So this is a system called BERT. And it's very famous from the NLP community. And recently, we also did similar searches with the question of like what's missing for images that can make masked autoencoding work. So in fact, we presented the MAE work in this year's CVPR, and in fact, it can work for images and pixels as well. So our pipeline is quite similar. So given an image as an input, we will mask out a portion of the image, and then we only feed the visible parts of the image into an encoder to get their hidden representations. And then this hidden representation will be concatenated with masked tokens together with the position embeddings, and then feed into a decoder for reconstruction. So, for example, reconstructing the entire target here. And MAE pre-trained encoders are pretty strong. So once we get the MAE pre-trained, we will just throw away the decoder and only keep the encoder for downstream tasks. So we transferred it to multiple tasks in that work. For example, object detection and semantic segmentation. And compared to supervised learning, contrastive learning, so MoCoB3 is a contrastive learning, and concurrent work also does masked modeling, we see strong improvements. And for MAE, it also works well for ImageNet 1K classification, image classification task, and achieved a state of the art back then. For our long sequence MAE explorations, we want to have a close look at the input specifications of image MAE. So the input of MAE is actually treating patches of a certain size as tokens. So this is following the vision transformer work that VIT is popular in computer vision. So if we have an image of size I, so for example 224 by 224, then I is 224, and we have a patch size of 16, then we will have a sequence length of L equals I divided by P squared, because it's height and width, two-dimensional. And then because MAE will mask out a lot of the patches for the encoder, the encoder's length is actually much smaller. So if we have a mask ratio of 75%, then the encoder's length is only 25% or a quarter of the sequence length. And of course, for reconstruction, the decoder is looking at the full sequence length because it has to reconstruct all the pixels. And our exploration has several highlights. So the first highlight is that we only change the pre-training input size, the input dimensions, and we will keep the transfer input fixed. So this is fair in comparison of computation complexity or model parameters during the transfer process. We will do some necessary interpolation if the size does not match. And this is also very different from, for example, model size explorations, because given a fixed size model, we usually, the size is the same during the pre-training and the transferring stage. And another interesting thing is that we actually have a deterministic relationship between all the three input specifications. So it's actually different for our study compared to other hyperparameters, because we cannot just change one parameter alone. We have to change two parameters jointly. So this is the way we studied the input specifications. And in order to make long sequence pre-training work, we have important or necessary design that minimally change the recipe from an original MAE. And this is to decouple the master size from the patch size of vision transformers or the encoders. So here is an illustration showing why this is necessary. So if we do not decouple the mask size and we have for example, a longer sequence by having a larger image size, then after masking, even with the same ratio, the mask pattern is too delicate to make it a more meaningful task. So instead, we can mask by gluing together 2x2 neighborhood in the encoder for the encoder, and it will actually, in the case of a 2x2, it will actually create the same or similar leveled a similar task in terms of difficulty compared to our original MAE. And for the default setups for our study, we pre-trained using a data set combining COCO train and unlabeled images. So these images are for object detection. We used encoder that's VIT based. And for transferring, we used COCO object detection, instance segmentation, 8020K semantic segmentation. And the important thing is that we fix the input specifications during the transfer. And we followed all the default MAE hyperparameters for fine-tuning the models for detection segmentation tasks. And for the baseline comparisons, we showed in this table. So we have the MAE baseline in the middle. We also included the BEIT, so that's another concurrent work to MAE that includes mask tokens in their encoder. And because we mask 75% of the tokens, this results in 4x of MAE in terms of encoder's computation cost. And in our case, we also have roughly 4x because we have 4x the sequence length. And you can see that different from BEIT, that's working a little bit worse than MAE. In our case, we see quite noticeable gains compared to MAE for these two tasks. And here I'm showing our main analysis among the three input parameters: sequence length L, image size I, and patch size P. And we first try to fix the image size or patch size, and we'll jointly change the two other input dimensions. And we can see that as long as the sequence length is changing, the performance is changing together with it. And when we switch to sequence length L, so we keep L fixed, and then we vary the image size I and patch size. For example, I think even for general pre-training, people have only looked at certain tasks in, for example, ImageNet linear classification I just mentioned. And it has one contribution, or actually contributions from BEIT as well, is that one contribution of MAE and BEIT is actually encouraging folks when they are looking at classification tasks, they should also look beyond linear classification to check the end-to-end performance as well. So I think overall horizon to look at more tasks to look at, and for me, I think definitely human understanding is a very important task, but we haven't really looked at that in the past. So it's worth checking the performance over there, and in the name of task-specific pre-training. I'm not sure I answered your question well.
Oh yeah, you answer indeed answered my question. So yeah, because for now, from the recent trend, I'm also thinking about the value of general purpose pre-training, or what should we do next for the general purpose pre-training. So last question from myself, what's your opinion about the recent progress in the vision language pre-training, and do you think it might be was trying direction, or
yeah, it's definitely progress, exciting progress over there, and I think it's very interesting to check and follow over there, yeah, and I think for vision language pre-training, there are certain tasks that we cannot do in pure self-supervised learning of images, or it's not so trivial to do. For example, zero-shot classification. So yeah, definitely interesting to check there, and it will bring different biases and different perspectives to our current tasks as well.
Okay, great, thank you. Yeah.
Hi, Xinlei. I'm Jiahao Xie, a PhD student from S-Lab at NTU. Thanks for your wonderful talk. I have a couple of questions regard to your presentation. First, self-supervised learning represented by contrast learning or mask image modeling have achieved superior performance than supervised learning. However, a recent work like DIT3 has shown that with a proper configuration or training procedure in supervised learning, it can also beat self-supervised learners. So, do you think self-supervised learners actually achieve stronger performance than supervised baselines, or whether the supervised learning will be replaced by the self-supervised learning in the future, or it still have a long way to go?
Mm-hmm. Yeah, so that's a good question. I think, I mean, I haven't talked too much about the advantage of self-supervised learning in this talk. So one biggest advantage of self-supervised learning is that it will unlock scalability. So if we have a large amount of data, and if we can have an infinite amount of compute power, then we can have a huge model trained on the data we have without human labels. And I think for supervised learning, if the number of annotations is limited, then it's very sensitive. It can be very sensitive to overfitting when the model becomes larger. So I think the biggest promise of self-supervised learning is scalability. So even if like supervised learning can beat self-supervised learning in some small data, small model regime, I think in the future, if we look at bigger data, bigger models, we may still have to switch back to self-supervised learning. That's my thinking.
Okay, thanks for your answers. Another question is also about the scalability of self-supervised models. As you have said, however, actually, mask image modeling method represented by MAE has shown scalability with larger model, right? However, some recent work has shown that it cannot be scalable when it comes to the data. So this question is also asked by some audience in the chat board. So do you think the data scalability of self-supervised learning still has some space to improve?
Yeah, definitely. It's a very important access to explore. I mean, I think we haven't really looked at the large amounts of data. Part of the reason is that we don't have that many compute as well. to do research iterations on large amounts of data. And there are a lot of infra issues, and for example, at Meta, we also have privacy issues and for data. But I mean, other forms of data, I think people have tried it already, right? Like for videos or for maybe 3D. I'm not too up to date over there, but it's definitely a very important access. I'll probably take more questions offline.
Let's take some questions offline if got chance. Thank you, Xinlei. Thank you so much for sharing today. Next, we will have our challenge briefing on PointCloud-C, which is the first challenge on point cloud robustness under corruptions. So without further ado, I will hand over to the challenge organizers, Jiawei and Dingdong.
Okay. Hi, everyone. I'm Jiawei Ren, and I'm from NTU Lab. I'm a second-year PhD student. So first of all, let me briefly introduce our benchmark, PointCloud-C, for benchmarking and analyzing point cloud perception and their common corruptions. So in short, we present a test suite, PointCloud-C, for benchmarking point cloud perception and their common corruptions. Our benchmark results suggest that point cloud perception is at risk of getting less robust. We discuss effective designs to improve the robustness. So firstly, we will discuss why robustness is very crucial in point cloud perception. Compared to other data formats like 2D images, point clouds as a raw data format suffer severe corruptions in the real world, like occlusions and sensory noise. Moreover, point cloud is widely employed in safety-critical applications such as autonomous driving. Therefore, the robustness to out-of-distribution corruptions is an important metric for point cloud perception. So how has the robustness been evaluated in existing works? So ideally, robustness should be measured in a standard way, like how classification accuracy is measured. However, prior research evaluates point cloud classifier robustness in many different protocols. So the protocol 1 evaluates the robustness to a selected set of corruptions, which cannot provide a comprehensive evaluation. In addition, different corruption selections make it difficult to compare across methods. Protocol 2 evaluates the robustness to the sim-to-real gap. Real-world corruptions always come in a composite way, not allowing fine-grained analysis. Besides, the sim-to-real performance gap couples with the domain gap within each category, which obfuscates the evaluation results. Protocol 3 evaluates the robustness to adversarial attacks. It measures the worst-case performance, but cannot reflect a point cloud classifier's robustness to common corruptions in the natural world. In summary, point clouds are used in safety-critical applications, but often suffer from severe OOD corruptions. Despite various ways to evaluate point cloud classifiers' robustness, there lacks a standard, comprehensive benchmark. Therefore, we present OmniBenchmark, a full corruption test suite to close this gap. So what should a comprehensive corruption set include? We provide a taxonomy of the common corruptions. We categorize them into 3 levels: object level, sensor level, and processing level. However, it is challenging to directly simulate real-world corruptions. Therefore, we simplify the taxonomy into 7 atomic corruptions. For example, background remain can be viewed as a combination of id local and lag global. How to design the corrupted test set? We designed the corrupted test set based on one of the most used benchmarks, ModelNet 40. ReasonWorks used the overall accuracy on ModelNet 40 as a gold standard for model evaluation. we corrupt the modernized 40 test set using the atomic corruptions with varying severities. So how to measure the robustness? Inspired by 2D robustness evaluation metrics, we use mean corruption error as the primary metric. To normalize the severity of different corruptions, we choose DGCNN, a classic point cloud classification method, as the baseline. Based on modernized C, we can provide a robustness benchmark. The benchmark result answers a critical question: are point cloud classifier getting more robust? Our answer is no. Although the accuracy of modernized 40 gradually saturates, the robustness is at the risk of getting worse due to the lack of a standard test suite. Then, what makes a robust point cloud classifier? There are 3 key components in the pipeline. So architecture design, self-supervised pre-training, and augmentation methods. Our benchmark allows us to understand the design choices of each component in a fine granularity. We observe that proper architecture designs can improve robustness. For example, advanced grouping and self-attention. Pre-trained signals can be transferred, benefiting robustness under specific corruptions. Mixing and deformation augmentations can bring significant improvements to model robustness as well. We propose a new architecture, RPC, and a new augmentation technique, Wolf Mix, strictly following our empirical findings. Both outperform existing methods by a clear margin, which verifies our observations. Besides classification, we further extend our robustness study to part segmentation in order to reveal more conclusions on general point cloud perception. We named the test suite for general point cloud processing as PointCloud-C. It contains two sub-test suites: ModelNet-C for point cloud classification and ShapeNet-C for point cloud part segmentation. ShapeNet-C is built in a similar way to ModelNet-C based on the ShapeNet parts dataset. It is corrupted by the 7 aforementioned atomic corruptions with 5 severity levels. We observed that for architecture design, GDA-Net performs the best, suggesting that advanced point grouping techniques improve robustness for generic point cloud perception. For self-supervised pre-train, point MAE shows a strong robustness, indicating that a proper implementation of self-supervised pre-training is the key. Finally, we come to our conclusion that calls for robustness in point cloud perception. The state-of-the-art methods for point cloud perception on clean data are becoming less robust to random real-world corruptions. Therefore, we highly encourage future research to focus on perception robustness so as to benefit real applications. Our code and project page are available at the link below. So based on this PointCloud-C dataset, we host our first PointCloud-C challenge. And now I will invite Lingdong to give more information on the challenge results.
Thanks, Jiawei, for the introduction of the PointCloud-C project. Now let me give you an introduction for the PointCloud-C challenge and also the final outcomes for this competition. And as has been introduced before, the motivation of this competition is that because the data in the PointCloud format are used in safety critical applications such as autonomous driving and robot navigation. So we use sensors to collect the data points from the real world scenarios under different complex conditions, for example, different weather and lightning conditions. So this data format often suffers from severe out-of-distribution corruptions. And PointCloud-C is the first competition that
targets the robustness of point cloud understanding under corruptions. Our benchmark results suggest that the point cloud classifiers are at the risk of getting less robust. So we highlight the importance of proposing new designs to improve the robustness. And so this is the taxonomy of our PointCloud-C competition. We have 3 levels of corruption sources from the object, sensor, and the processing levels, and 9 potential corruption types. It was mentioning that during the competitions, we combined several corruptions together instead of let them independent of each other. So our corruption set for this competition are more challenging. So we can see that the simplified the combination of these 7 autonomic corruptions, so we can have a more controllable empirical analysis. So for this year's PointCloud-C competition, this is also the first year we have hosted the competition at Coda Lab because it provides us the evaluation servers for evaluating the submissions. And here are some statistics for this competition. We have 32 participants from both the industry and the academia, and we have 13 registered teams with a total number of 270 valid submissions. Here are the a brief introduction of the results for our competition for both of the 2 tracks. We can see that the participants have achieved very promising results for both of the 2 tracks. For example, for the Modernessy track, we can see that the winner solution have achieved over 90% overall accuracy. And for the Shapnessy track, we can see that the winner solution has achieved over 83.6% IOU scores. And now let me present the final outcomes for this competition. The first place winners is from the Ant group, and the team name is Ant ECCV. So they win both the Modernessy track and the Shapnessy track. So let me rephrase the introduction of their methods. Our solution is based on GDANet, and we propose the robust k-nearest neighbor embedding fusion module to further improve the point cloud recognition robustness. To deal with the data imbalance problem, we combine with the generalized dice loss and the cross-entropy loss. We use batch renormalize during the inference phase to calibrate the corrupted data cloud distribution. So this video is from the winners, the first place winners. So let us just watch the introduction of their solution.
Hello, everyone. I'm going to talk about our solution for the 2022 PointCloud-C challenge. Our solution is based on GDANet. We conclude our proposal as follows. Firstly, based on GDANet, we propose robust KNN embedding fusion to gain stronger robustness in geometry disentangle module. In GDANet, the original KNN embedding is represented by top 1 feature, making the network quite sensitive to noisy data, and thus limit the model ability to a large extent. We embed the top K mean features of KNN clustering, here specifically top 3, top 6, and top 9 to enhance the model capacity. And the results show that the better KNN feature fuses, the more robust the network is. Besides, in part segmentation task, we also observe a severe class imbalance problem for small parts, especially in sophisticated objects, which might result in suboptimal solutions. So we introduce generalized dice loss together with cross-entropy loss for part segmentation task to deal with data imbalance problem. Lastly, during post-training phase, we apply batch renormalization to recalibrate the corrupted point cloud data distribution. And this helps to resolve the large gap existing between the training and testing data. Here in the table shows the ablation experiments of our proposed methods, as well as the comparison of our solution with other top solutions. We obtain an instance IOU of 0.836, exceeding the baseline by 0.052 for the path segmentation task. And for classification, we obtain an overall accuracy of 0.904, exceeding the baseline by 0.101. We rank the first place in both of these two tracks. Thank you.
Okay, so now let me present the second place winners. They are from DeepLink, and the team name is DGPC for ModernetC and DGPS for ShapeNetC. So for these two tracks, they propose two different contributions. For ModernetC, they propose a point voxel adaptive feature abstraction method. And for ShapeNetC, they propose GDANet, augmentation geometry disentangled representation. So let me rephrase the introduction of their methods. The proposed framework iteratively voxelize the point cloud and extract point voxel features with shared local encoding and transformers. Then adaptive max pooling is proposed to robustly aggregate the point cloud features for robust point cloud recognition. And I believe we have the winners online with us in this meeting room. So Li-Fa, are you able to, you can first unmute yourself and maybe give some words for the methods you used during the competition.
Hello, Leon, I'm here.
Okay. Do you need to share your screen?
Okay.
Yes, we can see your screen.
Okay. Hello, everyone. I'm Li-Fa Zhu. Our report is pure ADA, point voxel adaptive feature abstraction for robust point cloud classification. We are the DGPC team. Here are the members. The contents include the following four parts. First, the ideas. The ideas are inspired by the following two observations. First, the rough contour may benefit point cloud classification and corruptions instead of paying attention to detailed structures. Second, not all points in point cloud are equal for individual feature representation, such as plane points and outlier points. Here is the overall architecture of pure ADA. It takes point cloud X as input and outputs C squared Y. There are two modules, point voxel encoder and adaptive feature abstraction. In point voxel encoder, local encoding groups K nearest neighbors for each point, then learns D-dimensional point features FXE. Transformer is based on offset attention and residual structure. It generates enhanced point feature FST. Here, the input point cloud X is progressively voxelized twice with offset V and double V. Here, pyramid phase interaction is conducted as encoding 3. AFA module predicts point weight SXT here.
and conduct feature abstraction as the equation 4. The training set is mononet 40 training set. Validation set is the public mononet C dataset. Testing set is the private mononet C dataset. Overall accuracy and MCE of different models, such as mononet, PCT, GDAnet, RBC, and pure ADA, are reported in Table 1 and Table 2. Here, pure ADA achieves the best performance. Detailed results are also reported in Table 1 and Table 2, such as on different corruptions, such as jitter, scale, and others. Application studies on the proposed modules, such as the point also operation, AFA module, and positive tricks, such as best validation and some others, and some negative design modules are reported in Table 3 and Table 4. Model size and inference time are reported in Table 5. It's a small model and with fast speed. Discussion and conclusion. Equipped with a stronger backbone, better performance may be achieved in point cloud classification and corruptions. We can see here on clean mononet 40, MOA is 0.928. It's not high. Second, pure ADA is proposed for robust point cloud classification and corruptions, which outperforms the state-of-the-art published models. Third, point also encoder and adaptive feature abstraction are two effective components for robust point cloud classification. Finally, code is available at GitHub. Thank you.
Thanks, Ifa, for the detailed introduction of their point voxel adaptive feature abstraction methods.
Thank you.
So let's now, thank you. So let's now move on to the third place solutions. They are from the Beijing Institute of Technology, and the team name is BIT-GDXY-TXF. So let me rephrase the introduction of their methods. We fuse point cloud transformer PCT and point MLP for point cloud robustness predictions and take mixing and deformation augmentations to further improve model robustness. A simple model ensemble strategy is adopted and further boosted the final performance. So these are the third place winners. And also we have a Spotlight Award for this year's PointCloud-C competitions for the DGPC and the DGPS team, because they contribute a set of data augmentation combinations for various inferences and a set of parameter adjustment strategies to deal with complex point cloud recognition scenarios. And that's all for the competition side of the PointCloud-C project. So thank you, and we see you next time.
Thank you, Bingdong and Jiawei and the winning teams for sharing their solutions. So if you have any questions, the audience, you can just unmute yourself. And I have a question from myself for the second place winner. Do you think the voxel representation helps improve your performance?
Because for the point cloud understanding, there are several different representations for processing the data. And the voxel representation is one of them. And because the point cloud understanding tasks are divided into two categories, for the indoor things and for the outdoor things. The indoor things are mostly object-centric. For example, the point cloud of a plant model, of a bottle, etc. And for the outdoor things, there are very, because the number of points are extremely larger than the indoor things, and it's also suffer from the distribution, the imbalance distribution problem. So I think for these two different categories, the methods are also different, and the voxel methods are usually used for the outdoor things because it's a very efficient representation with the sparse 3D convolutions. And for the indoor things, most of them are point-based. They use, for example, MLP or self-attention to directly process the point cloud data. And for your question is, voxel-based methods can improve the performance. I think from the current progress, the answer is yes, because quite some of the methods adopt the voxel-based representations. But for the long term, I think the final accuracy is dependent on the resolutions for the voxels, because the voxel-based representations suffer from the resolution, because they need to divide the whole things into evenly distributed voxels. So we might lose some details for the overall point cloud. So we might need to also use other representations to complement this drawback of the voxel representations. Yeah, I hope this can answer your question.
Yes, definitely. Thank you, Lingdong. And if the audience has more questions about the challenge and the winning solutions, they can visit the PointCloud-C website anytime and follow up with the challenge organizers. Thank you, Lingdong and Jiawei. And next, we will have Yuanhan to introduce the OmniBenchmark and its two challenge tracks.
Hello everyone, thanks for watching this video. Today, I would like to introduce our ECCV 2022 challenge, OmniBenchmark, which benchmarks pre-trained model performance through the lens of racial rims. My name is Yuanhan Zhang. I'm from SLab NTU. First, let me briefly introduce our OmniBenchmark. The development of the large-scale pre-trained models, which are pre-trained on mega-scale data, brings great success. We are amazed at how this model can perform few-shot recognition ability in the open world. How to choose a good benchmark are largely discussed. In a recent study, researchers prefer the following two benchmarks. First, they want to use a universe dataset, such as ImageNet, as a good indicator for pre-trained model. However, the limitation of ImageNet is obvious. Its concept represents a limited spectrum of semantic rims in the world. Many rims are annotated sparsely. In addition, researchers would like to choose the CLIP benchmark, which collects evaluation datasets extensively. However, CLIP covering diverse datasets at the expense of subsumming datasets that have extensive semantic overlapping. For example, both CEFA, ImageNet 1K, VOC, CATAG has a concept birds. And if one model performs very good on the birds class on the ImageNet 1K, it may also indicate that it can perform good on CATAG. So evaluation on the birds class on the CATAG might be unnecessary. Based on this limitation of the current benchmarks, We aim to design a next-generation benchmark for evaluating the modern pre-trained model. We found that the ImageNet only represents a limited spectrum of semantic rings in the world. Many rings are annotated sparsely. So first, we build a much diverse taxonomy based on WorldNet, which is the label system of ImageNet. What we do is first integrate the public dataset into the WorldNet. Then we learn from another good knowledge base, Wikidata, and integrate most of their concepts into our taxonomy, and build this very diverse taxonomy. And as shows that for the most concept is a fine-grained concept which never showing in the WorldNet. Second, as clear benchmark covering diverse datasets at the expense of subsuming datasets that have extensive semantic overlapping, we want to get a line of datasets that solely represent a specific semantic. For achieving this goal, we propose to found those special tree roots in this taxonomy following three principles. First, we only retain the tree root with more than 20 valid concepts. And as shown that those concepts with less than 20 concepts was not be selected, like hunting dog and wild cat. Second, we only retain the tree root in the higher layer and the higher layer. So overall, in this taxonomy, only the mammal tree root are retained. And third, we delete the tree root that the majority of its concepts are related to personal information, such as people, and we also delete the tree root whose most concepts are not related to the natural images, such as chemical. Finally, there are 21 tree roots remain. Here, we name them as semantic rings, like here, mammal. Based on the above-mentioned strategy, we built a new benchmark for large-scale pre-trained model. Our benchmark focuses on evaluate model through lens of diverse visual rings. We thus name it as Omni-Ring Benchmark, shorted for OmniBenchmark. Here, ring means a group of semantic related concepts. Compared with ImageNet 1K, OmniBenchmark is diverse. Every ring includes more than 20 concepts. In the contrary, only 14% rings in the ImageNet 1K has more than 20 concepts, as shown in this figure. Then, compare with Click Benchmark. OmniBenchmark is concise. OmniBenchmark includes 21 different semantic rings. Concepts are not overlapped across the rings. For example, only the mammal have the bird's concept. Other rings don't have the bird's concept. In the contrast, all these four datasets has a class, the concept name bird. Based on OmniBenchmark, we evaluate 22 most popular models across different supervised signal, good model architecture, optimization strategy, like different regularization method, and training data. Various insights are observed. For example, we found that color jitter can largely hurt the linear probing performance on the bird rings, because the fine-grained difference between different bird classes come from colors, like these three kinds of birds. From the shape, they look the same. The model can classify these three birds meaning from their color. But if we use color jitter in the training stage, model can be classified unsensitive, can be unsensitive to different color, right? Then they can be hardly classify different color in the evaluation. Can hardly classify different birds in the evaluation stage. Beyond building the OmniBenchmark, in our paper, we also focus on how to optimize pre-trained model in a better way. As shown in the left, we show that the popular supervised contrastive learning framework, C, the limitation of this method is obvious. The built representation space lacks semantic inclusive bias, where semantically related objects should be encoded closer. For example, the distance between these two classes should be closer than Husky and the Ferrari, right? Therefore, we propose RICO, which encode semantic relationship in the negative sampling of supervised contrastive learning. Intuitively, instance race-related semantic meaning should not be pushed away. Like this, even though these two classes from different concepts, but because they all belonging to the semantic dog, so they should be encoded close in the feature space. And the semantic structure was being encoded in our taxonomy. From the performance on the Imaginal 1K and OmniBenchmark, we can observe that the superiority of RICO over other supervised contrastive learning methods. Based on the OmniBenchmark, we hold a challenge for ECCV 2022, and we also hold a leaderboard on the paper with code. We have a related challenge which proposed by the Google. Okay, let's briefly introduce the challenge of ECCV 2022. The OmniBenchmark challenge ECCV 2022 have two tracks, the academic track and the industry track. The academic track requires the pre-trained model only be pre-trained on Imaginal 1K. And in the industry track, your pre-trained model can be pre-trained on any dataset. Here, we recommend you can use or another dataset for pre-training data, then Bamboo. From the OmniBenchmark, we can show the superiority of Bamboo. It outperforms the ResNet 15 model pre-trained on Imaginal 1K for 11.1%. Okay, let us briefly introduce our Bamboo datasets. Okay, now let's introduce our work about our work Bamboo, building mega-scale vision datasets continually with human-machine synergy. The current construction of computer vision datasets mainly include two dimensions, label system and data annotation. Label system decides the overall diversity of your datasets, specifically how many categories your datasets will include. And the efficiency data annotation strategy can ensure you can annotate the most number of images under the smallest budget. For label system, WordNet, for example, WordNet is a commonly used large lexical database of the English, which is used as a label system for many popular datasets like WordNet. Though it was large, it was built in 2006, so it did not include many new words like iPad. And also, as we know, WordNet lacks many fine-grained concepts like this one. It's kind of the bird. Second, for data annotation, the OpenImage as an example is the largest publicly annotated dataset. But the biggest problem for OpenImage is its data might not very benefit to the society. What is this means? This means, for example, as Coco is a very good detection dataset for 18 common concepts. So why OpenImage also spend a lot of budget on concepts that Coco already carefully annotated, right? So for Bamboo, or Bamboo just aim to build a new dataset which cover more concepts, more diverse concepts, and ensure the new annotated data benefits the society at the most. Okay, so the first question we want to solve is how to get a diverse taxonomy, a very diverse concept. And we want to just extend the WordNet. So just as what I said in the OmniBenchmark, we also use the taxonomy, use our new built taxonomy, which extended from the WordNet. And as what I said, we collect the concept of public dataset and further extended it through another knowledge base, Wikidata. And in the Bamboo, we just use 3 solutions to integrate the new concept into the hierarchical tree of WordNet. And also, these 3 solutions are used in the OmniBenchmark. Then we annotate new data based on active learning. The model for active learning is trained on public data first. Based on the uncertainty of the model prediction, we can only annotate the web data that the model is uncertain, its category, or the data that is not included in the current dataset. Based on this strategy, we can ensure that new annotated data is an addition to the public dataset, which is beneficial to the current society at the most. Based on this active learning strategy, we built Bamboo datasets. The Bamboo classification part was 4 times that of ImageNet, and the Bamboo detection part was 3 times that of the Object 365. Besides, as we said, the newly annotated data is a huge addition to the distribution of the existing academic dataset. And we can say the new annotated data is mostly at this part. This part is the concept which never showing in the current datasets. You can just explore and download Bamboo data at this website, and you can try to download our Bamboo pre-trained model on this website. Finally, you can try to play Bamboo pre-trained model on the Hugging Face. Okay, thanks for listening. That's all my presentation.
Thank you, Yuanhan, for sharing OmniBenchmark and Bamboo. Yuanhan developed diverse yet concise benchmark for evaluating pre-trained models across various semantic concepts. And you can visit the OmniBenchmark website to explore the paper and its 2 challenge tracks. So now we will take a coffee break, and do come back in 30 minutes. After the break, we will hear from Professor Siyu Tang, and we will also have the challenge briefing of Panoptic scene graph generation. So see you later.
Hello, everyone. Hope you have taken a good break just now. My name is Zhong Ang, and I'm a PhD student at Lab at NTU. It is my great pleasure to introduce our next speaker, Prof. Siyu Tang. Siyu is assistant professor in the Department of Computer Science at ETH Zurich. She also leads the Computer Vision and the Learning Group at the Institute of Vision Computing. Please join me in welcoming Siyu to talk about her exciting works on human motion modeling and synthesis.
Hi everyone, I'm Si Yutang from ETH Zurich. I'm glad to be here to present the work from my group. And today I will be talking about human motion modeling and synthesis. So recent advance in computer vision and graphics has allowed us to build a very nice digital replica of the world. As shown here, one can reconstruct a nice 3D model of a landmark from a few internet photos. Also, embodied agents exist inside 3D environment, and such simulators allow us to train agents to perform tasks from this dynamic and embodied view. But if you take a closer look at this environment, a limitation of them is that they don't contain people. The reason such world contains no people is that it is very hard to fully automatically generate realistic people interacting realistically with the 3D scenes. And manually doing this requires significant efforts from artists. So the next question you might have is why generating realistic humans in 3D environment is a hard problem? Why can't we populate this digital world with realistic virtual humans? And there are several reasons. For instance, as shown in these examples, humans have different shapes, various clothing, and our bodies are highly articulated. And humans also interact with the 3D environment and each other in many different ways. So therefore, one of the research questions we are trying to solve in my group is how to model and synthesize realistic virtual humans interacting with the 3D world realistically in a scalable and efficient manner. So that brings us to the main topic of this talk, generative motion, human motion modeling, and synthesis. And I will present the latest works from my group and give you an example of how we use our generative motion models to inhabit a virtual village. Yeah. So existing solutions in character animation can produce controllable and high-quality human motion. However, based on our observations, the generated motion sequences are often close to training data and lack diversity, and also often doesn't have good generalization capabilities to diverse body shapes. In addition, using time series models for motion generation can well generalize across different body shapes and action types, but the produced motion is not realistic enough. So we can observe body floating, foot skating, and other artifacts. So to this end, in my group, we create data-driven generative models for generating virtual humans in motion in an automatic and efficient way. So our virtual humans have diverse body shapes, moves for a long period of time, and interact with the virtual world naturally. So here are the examples from our motion generative models. So our motion model is called Gamma, which stands for generative motion primitives via body surface markers. And the key idea of our approach include three parts. The first part is marker-based body representation. The second one is generative motion primitives. And the last one is goal-based motion control. And I will present these key ideas in the following slides. So the first key idea is that we represent 3D body motion with a sparse set of surface markers corresponding to those used in motion capture system. So predicting markers have several advantages. The first one is it can capture the full degree of freedom of body poses, unlike the commonly used skeleton representation, which lose the degree of freedom of the rotations around limb. And second, we don't need to separately infer body joint rotations and the global body translations, which is often a hard task. So we only need to model 3D marker locations, and these locations are in 3D Euclidean space. So it's like a sparse set of point cloud. And then we can leverage powerful statistical body shape models during the inference to directly get a valid human body back. So here I show how we use these marker-based body representations for motion prediction task. So given, for example, 2 seconds motion, and we want to predict 3-4 seconds future motion. It's not long-term generation, but like short-term future prediction. So in the nutshell, it is a conditional variational autoencoder with recurrent projections. So given the past motion of a person represented as 3D marker locations, as shown in the left figure, the encoder with the GRU encodes the input marker sequence into a latent code. And a standard way of predicting future motion is that the decoder will take the latent representation from the encoder, a random sample from the prior, and the prediction from the previous time step to generate 3D marker locations for the current time step, as shown on the right. The problem of such networks is that GRU tend to accumulate errors over time. So the predicted markers can gradually deviate from a valid 3D body, resulting in twisted torsos, foot skatings, and other motion artifacts. So to eliminate the accumulated errors, at each prediction step, we project the predicted markers back to the valid body surface. So to achieve this, we fit a simple X-body mesh to the predicted markers by optimizing this these objective functions shown in the bottom. So since the markers provide rich body constraints like controlling the full degree of freedom of limb rotations, and we start close to the solutions because we have a high frame rate and the fitting process is robust. So from our recurrent projection scheme, we not only obtain the regularized markers as shown here, but also realistic 3D bodies as shown in this figure. So here I would like to show you some motion that are predicted by our model. You can see, given the past motion of a person, as shown here in in green, our motion model is able to predict a diverse set of plausible and natural human motion in the future, as shown in red. So overall, our model is able to largely improve motion quality compared to the previous state of art when the paper was published. So the second key idea of our approach is this generative motion primitives. So what we have seen so far are motion prediction results, which means given, for example, a 2-second past motion, our model can predict, for instance, 4-second future motion. However, for populating 3D environment with realistic virtual humans, we need a generative motion model that can generate realistic long-term human motion, or in extreme cases, perpetual motion, right? So the motion should be controllable, should also be controllable, for example, by semantics. However, using neural networks to model a long-term motion, we see body moves unrealistically with, for example, foot skatings. You can see some foot skatings in the end of this generated motion. And we could observe more artifacts when we try to generate even longer motion, right? But on the other hand, we see that a shorter motion is easier to model for the neural networks. And also the generated motions is much more realistic For example, this 0.25 second motion, which we don't really observe much artifacts. So our key idea is that to model a long-term motion, or say a perpetual motion, we decompose it into motion primitives and model each individual primitives and then concatenate them. So our insight comes from the psychological studies where humans' reaction time to a visual stimuli is about 0.25 seconds. So it means that humans cannot control their body motion immediately after seeing a signal, but have to wait for 0.25 seconds to give a response due to the body inertia. So we let the motion primitives span 0.25 seconds. And in this case, it mainly contains unconscious body dynamics, which are shorter and more deterministic and easier to model for the neural network, recurrent neural network. So to be concrete, a bit more concrete, so given a motion seed, right, it could be like a marker location in the first frame or in the first two frame, our model first predict marker locations in the very near future, right, with uncertainty. So using a conditional variational autoencoder that introduces a latent variable sampled from a normal distribution. So by doing this, we can really introduce this uncertainty and generate diverse motions, right? And then the body regressor recovers the 3D bodies to fit the predicted markers. And the body regressor here is just a stack of residual MLPs. And with these extra models, the generative motion primitive models can run recursively, as the body can move perpetually without sacrificing motion realism. So here are the randomly generated long-term motion for different body shapes. And in our opinion, the generated motion is quite realistic, doesn't have much artifacts, for example, foot skating. And also the motion is diverse. Okay, so the next question is how to control motion generation process. For example, by some goals or semantic information like natural languages, right? So here in our work, we show how to control motion generation by waypoints on the ground. So here waypoints are visualized as yellow circles on the left. So to do that, we formulate the motion generation as a Markov decision process, which includes the states. So which are the body motion seat, like initial position, as well as distance to the goal, so the waypoints. And we also have the model, the motion model, which is the generative motion primitives models we have seen in the previous slides. And then we also need to define the action. And in our model, the action is the latent variables of the generative motion primitives model. And then we also have a policy, which is a neural network mapping from the states to action. And without control, right, without this policy, our body moves randomly and ignores the waypoints. So on as shown in the left video, right? It completely ignores the waypoints, just do some random motion because we have this latent variable sampled from normal distribution. Okay, and here we show how to introduce motion control part into our generative motion primitive models, right? So this is the model I showed you before. We have a latent variable Z. So our generative motion model generates random motion sequences by introducing this latent variable Z sampled from this normal distribution. And to control the motion generation, so inspired by this motion VAE paper, and here we introduce basically a policy network. And here you can see the difference between the two models is basically we introduce this policy network. And also the state now is not just the body marker locations, initial body marker locations, but also the goal location G on the ground plane, right? So our waypoints. And the latent variable Z is now regarded as the action to generate the current motion primitives. So the generation is conditioned on the goal, and the action is produced by this policy network, right? And to train that, we need to define reward, and our reward include the path following reward. So the virtual human should try to follow the path from the initial position to the target location. And also body orientation reward, valid body pose reward, some body pose prior, and goal reaching reward. So if the policy can reach the final goal, it should get some high reward. And with this reward, we can update the policy network using the PPO algorithm in the advantage actor critic framework, right? So importantly, we use a motion prior loss to regularize the policy output in order to produce realistic human motions, right? Okay, so this is our RL algorithms. And how does this policy gradually learn? And you can see at the epoch 0, where we just have we don't have really a policy network to predict this action Z, and then our motion model completely ignores the waypoints, right? All the virtual humans just randomly walk in this 3D environment. And when we start to try to train the policy so that it makes the virtual human reach the goal, you can see in the beginning of the training, some virtual humans ignore the goal and some produce weird poses and unnatural motion. And with training progresses, you can see the virtual human now really try to reach a goal, but still with unnatural human motion. And when we reach epoch, for example, in our model 250, the motion becomes better, but still not ideal, right? And then when we reach the epoch 500, the model start to produce nice random motions that are all try to reach the waypoints, right? Okay, good. So in the end, you can see our model is scalable and controllable and generalized to different body shapes. So here are all different identities: tall, short, big, small, right? Body shapes. And you can see we have this motion is really different for different person, in the sense someone really try to rush to the final goal, and someone the last two person looks like really wandering in this environment, right? Okay, so that's about a goal reaching human motion generation in 3D environment. So I will come back to this example in the end of the talk. But now what I want to show is another work which synthesizes human-scene interactions, right? So here I want to introduce our latest work that synthesizes fine-grained human-scene interactions with semantic control, not just walking, but also touching furniture, sitting on the bed or sitting on the chair, perform different actions, right? Okay. So in this CVPR 2022 work, we present a method to generate 3D human-scene interactions with semantic control. So previous work on human-scene interaction synthesis can put people into the scene with in physically plausible ways. However, they lack mechanism to control the high-level semantics of the generated interaction. For example, sitting on a sofa or lying on a bed. So incorporating and controlling such interaction semantics is critical for creating virtual humans with realistic and interpretable behavior. So to this end, we introduce CONS, stands for compositional human scene interaction synthesis with semantic control. So given a 3D scene and interaction semantics, so this is a 3D scene, and where the interaction semantics is sit on this chair and touch the table, right? So our method generate a human body performing the specified interaction. So we represent this interaction semantics as a set of object action instance pairs, right? Touch, table, sit on chair. And our method first generates the body PEVX frame, which corresponds to the where the interaction occur. And then with the PEVX frames, our method then generates the detailed body performing the specified interactions. So to be more specific, we introduce a conditional VAE model for both body and PEVX generation. And here we use body generation as example. So the object token edit as edit with action embeddings are the conditional inputs to both the encoder and the decoder, right? So this point at represent the object. And the transformer are used to encode the object surface points and the human body vertices, body surface vertices in a unified latent space. And the decoder outputs the post human body with contact features from the sampled latent code. And at the generation time, only the decoder and the conditional information are used. So here I show you some randomly sampled result, right? So you can see like these are the results we randomly sampled for the interaction like lie on the sofa, right? So you can see like we can generate virtual human bodies that lying on the sofa. And then here is like touching the chair, right? So we have different here even with the back to touch a chair, right? So these samples are not perfect, but we think the results are quite robust in unseen 3D environment. So all this environment and objects are unseen during the training, right? And also the generated interactions also show the some diversity, right? For example, touching chair here. So our model, this compositional human interaction synthesis model, has a few very interesting extensions, right? So first, we can explicitly control the shape of the generated human bodies because we take the template body as part of the input, right? And then basically by explicitly specifying the body shapes, or using different body templates, we can basically explicitly control the generated body, the shape of the generated human interaction, for example, for bigger person or really for like a small person, right? And the second one is we can also generate compositional interactions by only training on atomic interactions. So for example, in this case, our model never seen examples of standing on the sofa and touching the light. However, by leveraging the attention mechanism of the transformer architecture, we can generate the action for standing on the sofa and touching the light without really seeing such training example before, right? So you can see the body has some weird poses to touch the lights, but it's really try to really touch the lights. And the key is to leverage this attention mechanisms of the transformer architecture. Yeah, for more details, please check the paper and the code is available. So the following results are for architectural designs, which are not included in the paper, and now with additional carefully designed data augmentation method, we can populate this nice 3D environment with virtual humans in a scalable and controllable way. So for instance, given this sleeping room, we can specify lying on the bed and touching the bed, and we can generate realistic virtual humans, right? And here, like walking on the floor, touching the sofa, sitting on the sofa. And here is a dining room, and we specify like sitting on this chair, and then we generate virtual humans sit on the chair, and even standing on the chair. And yeah, so diverse body interactions or standing on the sofa. Okay. So the next topic I want to talk about is hand object or human object interaction. Right? Human not just interact with big object, we also grasps object, right? And then for like hand object manipulation or hand object grasping, we also have a few projects. Right. So the very first project was published 2 years ago at 3DV 2020, and it's called Grasping Field Learning Implicit Representations for Human Grasps. So like there are many related works for grasping synthesis or grasping recognition, right? In robotics, in computer graphics, as well as in computer vision. So our key observation in this work is that human grasps is rooted in physical hand-object contact. And through this contact, humans are able to grasp and manipulate objects naturally. So to better model hand-object interaction, we must find a way to effectively represent the contact between the hand and object. So that is really the key insights. So based on this insight, we propose a new interaction representation back in 2020 that is based on regressing a continuous function that we call like a grasping field, right? So the grasping field maps any 3D point like XYZ to a 2D space where each dimension of the 2D space indicates the sign distance to the surface of the hand and the object respectively, right? Nowadays, this concept is very popular, right? Like this coordinate-based representation, right? And in 2020, we basically leverage this concept for grasping synthesis. And in this way, the contact and the interpenetration relations between the hand and object can be explicitly represented. So we further use the deep neural networks to parameterize the grasping field and learn from data. As a result, the learned grasping field serves as a powerful representation to facilitate hand-object interaction modeling, right? And also this learned grasping field can be considered as an interaction prior, which enable us to infer various grasping poses of hand and only based on 3D object. And here are more details, right? So for example, for the interpenetration area can be represented by the grasping field directly, which means like the output of the grasping field is like both are less than 0, right? So that's the interpenetration. And for the contact area are the grasping field, like the 2-dimensional both equals to 0, right? And when there is no contact, then the distance of this point is basically to the hand and to the object are both larger than 0, right? So by doing this, both the surface of the object and surface of the hand, as well as their interpenetration contact relations are represented in a unified way in this grasping field representation. Okay. So by leveraging this grasping field representation, now we can do grasping generation, right? So what we do is very simple. So given a training example, a pair of hand grasping object, right? Static hand grasp object. We use PointCloud encoder to encode both hand and object. And then for the decoder, we use grasping field to decode for every point in 3D space, the distance to the object and distance to the hand. And then during the inference, we only take the object as input, and then we use our grasping field to infer like the potential grasps, right? So here are some results, and you can see like the synthesized grasps looks pretty nice, right? And nowadays there are much more baselines, because lots of people are also working on these problems. And by then, like we only have very limited baselines, right? And our result achieve at that time state-of-art result. Okay, good. So that is only like a static grasps. So in our latest work, we try to generate grasping motion, and not just the hand grasping motion, but the full body grasping motion, right? So in this ECCV also 2022 work, we propose Saga, a framework to generate diverse, realistic whole body grasping motion sequences that approach and grasps a given object. And Saga stands for stochastic whole body grasping with contact. So object as motivation before, right? Like object manipulation is one of the most common and important activities in our human daily lives. And synthesis, human grasping motion, has many applications in AR, in VR, in video games, and maybe robotics, right? So in this work, given an object placed in 3D space with different positions and poses, for example, this position, different positions, poses, and given a human initial pose, right? We aim to generate diverse motion sequences to approach and grasp this object. And here are the generated motions from our model, right, on unseen object. So just very briefly, the model. So in a nutshell, we build a two-stage method to address this problem. So conditioned on the given object information, at the first stage, we generate diverse grasping ending poses, right? And then given taking the generated ending poses and the given initial pose as input, at the second stage, we infill diverse in-between motions. So for grasping pose generation, we use marker representations of the body as shown here, and we build a multitask conditional VAE to jointly learn both the body marker positions with contact map and the object contact map, right? So both the contact map for the on the hand and on the object. And for the second stage, for the grasping motion in feeling here, right, we build a hierarchical CVE model to generate both the global trajectory and feel the local articulation motion in accordingly. And also predict hand-ground contact information. And finally, with the generated like marker sequence as shown here, together with a hand object and hand human ground contact information, we can recover smooth and realistic grasping motion sequences, right? And here I want to show you the randomly generated ending pose. So so this object are unseen during the training, and it also have different heights in 3D space, and you can see our model can generate pretty good ending poses, and these are all random samples, right? And here are some random samples of grasping motion, right? As we said before, right? The first step is to generate the ending pose, and then we use a CVE model to generate diverse in between motion. So this motion drives the initial pose to approach and grasp object. And all the examples here are just random samples without any cherry pick, right? Okay, good. So the last example I would like to show here is like our exhibition. It's like how we really leverage our motion, generative motion models to go beyond like scientific contributions, right? Like to make a bigger impact by doing this exhibition together with architects. So now our exhibition was at the Guggenheim Museum in Bilbao, and we do it together with the Grammatik and Color Research from the Architecture Department of ETH Zurich. So what we did is we populate a virtual village with autonomous virtual humans, showcasing how to use generative motion models, data-driven generative motion models in future metaverse applications. This work was led by Yan Zhang, who is a postdoc researcher in my group. Okay, yeah. So here are some results from our model, just to have a closer look at the result. And here I want to show you a video which we made to to show you the background story of this exhibition and also of our motion generation models.
We've been invited to participate at the exhibition, the Bilbao Guggenheim, by the Norman Foster Foundation, and there we decided to revisit the Flight Assembled Architecture exhibition project. Flight Assembled Architecture was commissioned by the FRAC Centre in Orléans in 2012. We decided to produce the installation of a city, an ideal city, an utopian city that would build upon circularity of movements, of mobility, and circularity of construction. We built a 6-meter tall model and scale 1 to 100 in real time during the exhibition with the help of drones. We took the chance to revive this utopian project by injecting life into it. Life by virtual avatars that inhabit this virtual utopian project. Now, this project we do in collaboration with Professor Xiu Tang that has developed artificial humans that have their own behavior and react to the virtual environment around them.
At the Computer Vision Learning Group, we work on computer vision, specializing in perceiving and modeling humans. For the FAA Revisited project, our goal is to populate a large digital environment where virtual humans has different identities, diverse body shapes, move and behave naturally in this environment. So we implement efficient and scalable motion generation models that can generate 200 virtual avatars in real time in this large digital environment.
In the exhibition, the visitors can actually witness all these avatars. And also they can take a look at the first-person perspective of these digital humans perceiving the spaces and the vertical village. This, I think, is very interesting because it points towards a future where architecture can first be tested by being virtually inhabited before it's actually built. This is a completely new reality to the design of architecture. And I think this project was particularly valuable for the different research partners because here computer scientists and architects worked very closely together and the groups learned a lot from the individual methods and how they combine into a future of taking the virtual as a reality in the design of architecture.
Yeah. So as mentioned in the beginning, one of the research questions we are trying to address in my group is how to model and synthesize realistic virtual humans interacting with the 3D realistically. And so far, what I have shown to you are our latest generative motion models that are scalable and controllable, right? And for the future directions, we will explore how to combine this with perception, with capture, and how to build personalized and dynamically updated motion models for perceiving, for like modeling 3D humans in 3D environment. Okay, so these are the PhD students and postdocs in my group, Computer Vision Learning Group at ETH. So this work cannot be done without this amazing, my amazing collaborators. So the code and model and the data of published work are available on our website. So please feel free to use them. And thank you very much for your attention.
Thank you, Siyi. Thank you so much. It's very exciting to see your group's works on modeling humans, human motions, and the generative human models. Perhaps now we can take some questions from the audience. So if you have any questions for Siyi's talk, please feel free to unmute yourself.
Hi, Professor Siyi. I have a question about the human-machine interaction.
Yeah?
Hi, Siyi.
Yes.
I have a question about the human-scene interaction. How the model will deal with the objects that appear in the test but not exist in the training data? Yeah, which the avatar will respond. For example, if we want the avatar to sit on the sofa, but the sofa, this object is not exist in the training data.
Okay. So for the paper, right, we always split the training and the test thing. So the training thing and test thing are different, meaning the training object and the test object are different. So, but they are similar, right? It's not like a big difference, but they are similar. But so basically the model works on the object which were never seen before during the training. And the reason it generalizes because, for example, we use this PointNet encoder to encode object, right? So we have learned modular to try to do generalization. And then for in order to make the model really generalized to a different domain, for example, in the talk I showed this result on the synthetic data, not synthetic data, but really cleaned 3D CAD models. For doing that, we had to do like a lot of data augmentation, like retargeting, so that we can generalize to this clean CAD 3D environment. Yeah. I don't know whether this answers your question or not.
Yeah, that answers my question. Yeah, thanks for your response.
Sure.
I also see a question from the chat box from Jiawei. He says, hi, Siyu, physics like gravity and contact is an important property to make human motion generation realistic, particularly when interacting with the environment. Which way, in your opinion, would be more promising to model physics in motion generation? Explicit modeling or implicit modeling?
Good question. So far we ignored physics, right? So we have optimization, like for example, in the human-scene interaction work, we have optimization step where we define like physics inspired losses, for example, interpenetration contact loss, to make the prediction or the generation more physically plausible. But we never really like make it like really physical plausible, right? There's still like it could, like the body could have interpenetration with the environment. That happens. So I think physics simulations is the way to go. Yeah. But we don't have any published work in that direction yet. But I think that's probably the way to go.
Yeah. Thank you. And any other questions from the audience? There's another one from Mingyuan.
Okay. Let Mingyuan go first. Yeah.
Okay. Then Mingyuan and Zhongang. Mingyuan says, thank you for your wonderful talk. I'm really interested in the work about modeling the human-object interaction and the human-scene interaction. My question is that, can we exploit knowledge from text-driven motion generation models into the 3D scenes so that we can generate more diverse motions? For example, like taking a shower in the bathroom, turning off the TV, and so on. I'm wondering, is it possible to generate these actions which are not included in the data set using the prior knowledge? Yeah, that's Mingyuan's question.
Yeah, good question. So that are all really exciting research questions, right? So we are of course also exploring, and I think people like these days they are like text-driven motion generation. There are like works shows very, very good results, like impressive results. So I think the field is really moving towards that direction. And then another aspect of the question is, if we don't really have for example, for many human-scene interaction motions, we don't really have the training data, right? And how do we do that? So my current thoughts is I think use RL. So like right. So for example, for our current motion synthesis work, like the waypoints, right, could be anywhere on the ground. And it's really go beyond the distribution that we have in the training data. For example, if you use AMAS, and then like most of the time you have to define the waypoint that really like people already facing the waypoint. But in our demo or in the architecture like these applications, it can happen the waypoint is behind the body, right? And then how do we generalize our motion model to such like out of distribution goals? So we use the RL, and so it's basically about using RL, using reward to teach the agent to do something that is beyond like really direct supervised training data. And I guess like if your reward makes sense, if you define really good reward, and then potentially you could teach your model or your virtual humans to do something that is not really that doesn't exist in the training data. That's my guess. I don't have a clear solution. Oh, sorry. Yeah.
Thank you. And just now, Zhongang is having a question.
Hi, Prof. C. Thank you for your wonderful talk. My question will be a bit general. Since you are doing human-C interaction, and we also see there are some great works recently on human-C interaction and generating human motions in a scene. I'm just wondering, are we, because this is a good foundation for us to move forward and maybe towards interpersonal interaction. And do you foresee this is going to happen?
Yeah.
And if it is, and what are the challenges, and what are some things that may intrigue people about doing this?
Yeah. So first of all, like people really like there are works about synthesis human motions in 3D environment, and so I don't have an exhaustive list of all the works, but I think so the quality like still can be improved. Like this work, we are really like still I think we are really at the like we'll have preliminary result, right? Not really like high quality. If you think about like the motion from AMAS, right? It's really high quality captured. And then the question is, how do we generate motions that really reach that type of quality, right? So I think there are still lots of work can be done in that direction. And also that links to the previous question, like about going beyond the training data, going out of like a training distribution, like actions, right? So there's lots of works to be done. And but for the person-person like interaction, that's I guess your question made about. I think that is like I think that is also the same thing as a person-scene interaction. So we don't have training data, right? Like you can capture data, but like can you really get a person-person interaction data that is like as big as AMAS, right? Or like a person-scene action data, the quality and the quantity as big and as good as AMAS? I think it's really a big question. And then now the question is, without such high quality, large scale data, what do we do, right? And from what I see, right, I still think RL is also a solution for this person-person interaction, right? So by defining the reward, how do we really introduce a prior knowledge, right? Like, and also, but I think that's probably like the way I would go.
Thank you very much.
Sure. Thank you. Maybe we have time to take one last question. There's one question from Jinglu Zhang in the chat box. It says, "Thank you, Prof. Tang, for your excellent talk. I have some questions about this talk. Could you talk further about the future of RL in virtual human, more others in 3D things?"
Future.
It's quite a broad question.
Yeah.
About future directions.
So I don't know the future of RL because, but I think RL has a future for virtual human, for generating virtual humans, generating realistic behaviors. So, but like we all know, it's hard to train, right? So then the question is, how do we really? Are there anything we could explore, like to make like the training more data efficient, easier? For like, for example, for human motion generation, scene interaction generation. I think those are all like research questions to explore.
Yeah, that's true. Thank you so much, Prof. Tang, for being here today. We hope to see you around. Thank you so much.
Thank you.
Bye. Thank you. Bye-bye. Okay, so next we will have Jinkang to introduce the PSG challenge, which stands for Panoptic Scene Graph Generation. Without further ado, I will pass the time to Jinkang. Hi, Jinkang, are you here?
Yes, I'm here.
Okay.
So
hi.
I'm here in Tel Aviv. So I can change my virtual background to was easily replaced. Can you hear me clearly?
We can hear you. You are outside, actually.
Yes. You can see where I am.
It's good to see the atrazine in Tel Aviv.
Yes. So it's easy workshop. So if you see the background, you can see you are really attending ECCV. Just things here, and we gotta talk about what the PSG challenge currently like proceed. So PSG challenge, we totally have 100 teams and participants about 459, and the prize is very big, huge. Big thanks to the sponsor from Hardware Lab who organized the international algorithm case competition. So we will have one champion with like $90K US. It's like RMB 60 or 600,000 RMB. And we have two second prize and the 5 third prize. And so now the primary round ends and top 20 teams are selected to verify their methods. We are still working on that. And top 15 teams will be proceeded to the next round. And the shortlist will be released very soon, like 2 days later. And here are 20 teams that we selected, and 15 of them will proceed to try to get that much money. So today we're going to briefly summarize the task, and then some of our top teams will share their insights on I cannot believe it cannot work well, because the competition is still not end. So we cannot ask the participants to share their results yet. Maybe in CPR workshop or something later we're gonna share. But now we're gonna have interesting discussion on some methods that cannot work, that we cannot believe why it cannot work. So what kind of scene graph generation is like? The task is that we take in an image with complex things, and we hope the model can output a scene graph with Panoptic segmentation. So different from the classic scene graph generation task, Panoptic scene graph task, we use maps to ground the objects. So we have an accurate grounding, and also the class granularity will be more proper and able to involve background. So it's an advantage over the previous scene graph generation task. And we hope in the new task can guide the community to understand the scene better. And why we propose PSG is like we hope the PSG model can empower the visual reasoning and the relation aware image generation. And we also hope scene graph can be a good like good protocol between good bridge between deep learning and symbolic reasoning. So yeah, so we hold this task and hope that the participants can give us many more interesting and like very strong PhD models. So yeah, the PhD data set, we have almost 50K images and 80 objects and 53 staff. Totally have like 56 relations, and they are carefully annotated. And the metric is a record K and mean record K. So a successful record requires both subject and object. You can see, for example, these two people. So a successful record needs this person. The mask of this person is accurate, and the mask of another person is also accurate. And the class of the objects and the class of the relations are all accurate. So the demanding of the record is very high. So it could be a very challenging task. So now I gotta invite our participants to share their insights. I cannot believe it cannot work well. So some insights when you're doing the competition, you can share your insights. And so first we're gonna ask Zijian. All right. Can you share something about I can share cool things you try? Yes, you can.
Can you see it?
Yes.
Okay. Actually, I'm in the hotel. Today I will share an idea that is not work very well, but it is a very common sense. I think it will work very well, but it not. Actually, as for me, it was not work very well. And this is the SOTA method published in the Panoptic sense graph generation paper. And we can all know that in this paper, wait a moment, the prediction for the subject, object, and their relationship is predicted in parallel. So, but in many papers, especially in the multi-phase and other papers, we all know the relationship is between the subject and the object. So I think if we could first predict the subject and the object, especially for the object and their information, for example, their class and their masks and the bounding box, we use this information to predict the relationship between them. They will get a much better results. So my idea and my motivation is very common and very easy to catch up. Is that for the sense graph generation task, we can first to predict the object, and then we predict the relationship. So I want to make a model just to implement this. Yeah, this is the method. I just to add a transformer decoder behind the original PSGTR. For the first transformer decoder, I use it to predict the subject and object and their information about the bounding box and the masks, and then use the second transformer decoder to predict the relationship between them. And there is another thing is about for Panoptic sense graph generation, we have the masks about for each object. So I add the masks in the transformer decoder with the mask attention. I think this will help the second decoder to focus on the two objects, and these two objects can give a more better relationship. But the result is not very well. I used the evaluate pen relevance equals to true and test this result on 1,000 validation set. The first row is the baseline. And the second row is the result. We can see there is a decrease. But but I really don't know why, because I add some parameters and I also train it very well, but the performance is not very the performance decrease. And I also know this is another method published in the PSG paper. I think this is also another kind of object first and then relationship, because we need to predict the objects and then use a selector to determine what is the relationship for each relationship, what is the object and what is the subject. So I think this is another kind of object first and then relationship models, but the performance is also not as good as PSGTR, especially for when we train the model for 60 epochs. So for this not to work well ideas, the first question is our intuition is wrong, and or we don't have find a very good method to better use the object information to predict the relationship. But in my mind, I still believe we can find a better way to make it, because for many sense graph generation method, we're only using the two-stage method. For example, the VC tree and the multiphase, they are all two-stage method. So I think maybe we can find a better way to deal with, but I'm not find a better way now. Okay, that's my share.
Thank you. Okay, Zhijian, for sharing. Yeah. So yeah, and we hope that when the competition ends, we hope that there are some methods showing that the two-stage or the object first and then relation, this kind of the work can appear, right? So
okay,
yeah, a good exploration. That's great. And then we gotta invite Bizhe, right? You can unmute yourself and
up here. Okay, let me share my screen.
Yeah, you can share.
Okay, can you see my screen?
Yes, I can.
There's two casting in my first slide, sorry. Yeah, so hello everyone, I'm Bizhe, and I'm a first-year master's student in the University of Queensland. So thanks for Jinkai giving me a chance to share what I found on OpenPSG. And today my topic is I cannot believe clips does not work. By the way, these are two cute cats in my lab. And for anyone who does not familiar with OpenPSG, OpenPSG focuses on two problems. The first problem is segment objects in the image, and the second task is generate relations or predicates between objects. My idea was given the predicted triplets, which combined by subject, predict, object, using clip to do prompt inference to correct some wrong relations exist in the predicted result. Here is an example from OpenPSG dataset. The left side is original image. The right side is the image Panoptic segmentation result. And the words in the middle are the subject, predicate, object triplets exist in this image. So there are 6 triplets exist in this image. So the first idea is using prompt inference to correct object words in the triplets. So the object word is the last word exists in this sentence. And the three prompt templates I tried are person beside something, person stand on something, and the person holding on something. I concatenate every possible objects to the end of them to form a sentence and feed them into clip along with the images to predict a confidence level. Among those prompts, only the last one is correct, which is a person holding umbrella. The rest of 2 are wrong. However, the potential good news is for those 2 wrong prompt prediction, the confidence level is quite low. For example, This one, the person beside an umbrella, the confidence level is around 0.2. So their confidence level is quite low. And the second is using CLIP to correct predicates between subject and objects. The prompt template is combined by a subject and an object, and I insert all possible predicates in the middle of them to form a sentence and feed them into CLIP along with the image to predict a confidence level. However, CLIP does not make correct predictions on these three templates I show in the red word. This result quite surprised me because I expected CLIP to learn the concept of relation between object and the subject and the object from the 300 million images and the text training data. But I believe that this direction could be a potential solution. The bad news is some other participants told me that he has already tried the CLIP on the OpenPSG, but the mean AP is quite low. But I still believe this could be a solution for the triplets in the OpenPSG. So that's all my share.
Yeah, thank you, Peter, for your great sharing. Sounds very strange that the CLIP cannot solve the prompting or the blank filling task that you generate for them. So yes, and sounds like of course your solution sounds very reasonable, but yeah, it's a surprise that CLIP cannot solve. So yeah, maybe try another prompt or something like that. I'm not sure. So yeah, we can discuss more. After the competition ends and see any good results there. Okay, yes, thank you, Peter, for your. Yeah.
Okay, can I have a word? Yeah, I observed that CLIP is usually to predict, for example, if I have a subject and predicates, CLIP always predict something nearby them. For example, the person beside. For example, like the person is holding an umbrella in this example. So this is correct because I think the CLIP is predict the last one by the distance. For example, the first one, you can see the true the CLIP result is person beside the umbrella. However, the true relation is person beside the person. I think the CLIP is predict by the distance of the objects. So that's not quite good.
Okay, get that. So, but yeah, but like PSC, we also have the mask information. Maybe we can also use that. But anyways, we can explore them. So next participant. Let's share. So who is the next person to share? Let me check. Nikki, right?
Okay.
Yeah, please start.
Okay, can you see?
It's not a presentation mode. It's kind of it's a mode that you can see.
Okay.
I can see several screens. Can try another time.
Sorry.
Yeah, just now it's like we were able to see the subscripts for the presentation. Yeah, now it's good.
Yeah, that's great.
Okay. Yeah. Okay. Hello, everyone. Today, I'm going to share with you an idea that looked good but failed in the PSG challenge. The Panoptic scene graph generation task aims to interpret a complex scene image with a scene graph representation, with each node in the scene graph grounded by its pixel-accurate segmentation mask in the image. So, okay, Clip is a neural network trained on a variety of image test pairs. Given an image without directly optimizing for the task, Clip can match the performance of original ResNet 15 on ImageNet zero shoot without using any of original labeled examples. So, how can we apply the power of Clip to PSG tasks? The intuitive idea is that for any two masks, we can construct a series of queries: subject, relation, and object. Then calculate the cosine similarity score of the image and test queries as the prediction result. Okay, let's take a look at the experimental part. The record 20 result of the zero shoot on the left is 0.0667. Although it is inferior, but it shows that the clip is still somewhat effective. In the middle, byte size equal 320 is used to fine-tune, and we find that the mean record 20 improved slightly. On the right is to increase the byte size to 7,000 to 7,680. Still, the mean record has improved, but the effect is still poor. So why it doesn't work? I think there may be two reasons. First, our fine-tuning data is only tens of thousands, which may damage the original feature. A more reasonable approach may be add a fully connected layer and freeze the backbone for the training. Second, the original training byte size is 32,000. We are limited, but we are limited by the computing power, and the maximum can be only 7,000. Okay, this is the end of my presentation. Thank you for your listening.
Thank you for sharing. Also, you also cannot believe Clip cannot work, right? So yeah, that's a very interesting way to explore, and we hope that someone can make Clip work. And yes, so we have the last person to share.
Okay.
Yeah. Yes. So you can share whenever you are ready. So
I'm here.
Kaijie, right? Okay, you can share your screen whenever you are ready. You
Okay.
can click the button. Yes. Great.
And can you see?
Yes, I can see the it's not the presentation mode, but you can photo in this mode. Anyways, you can talk in this mode. So it's not a presentation mode.
And hello everyone. And today
Yes.
I want to share why waiting doesn't work and this challenge. And I must be saying my English is not very good. I can only read the tag of the PowerPoint. And we can see the statistic on the number of the relation category. And the number of the top category is almost invisible. You can see the tall category and it's very small. About resampling resampling is early study also include undersampling of the head category and oversampling of the top category. However, the essence is that the sampling frequency of different category of image evolves way according the number of sampling. So in recent study, we can call collective then resampling. The more common strategy is also called cross-balance sampling. And about reweighting, many more complex types such as object detection and instant segment prefer to use weight loss to solve the long-tail distribution problem. After all, when a single image contains multiple objects to be detected or segmented, sampling then separately by category is far more cumbersome than sampling that at the image level. And the improvement of the reweighting is not only simple, but also tend to be more feasible. And we use the calculate the average value of object, subject, and relation class. Then number of each class is divided by the number of the average. To obtain the reweighting R. R is multiplied by the log of each class. You can see in the two image in my trade data trade log. We can see both the above method will fail in the case of too severe long-tail distribution. Too many duplicate image cause the network to be seriously overfit for the top category. The result is that the accuracy of the head prediction and the accuracy of the top drop simultaneous, and the validation set rise. You can see the rise in the depot when. Okay, thank you. In my share.
Thank you. Yes, I believe that the PSG data set also has a very strong imbalance problem. Severe imbalance problem, yes. But yeah, we do need to solve that. You get a very high score. Yeah, but reweighting maybe not a best one. Maybe some other like a law, something like that. I can solve it. Anyways, yeah. So we're gonna look for the participants solution when competition ends. So yeah, thank you all for sharing. And
thank you.
Thank you. So I guess that's all the sharing from PSG competition. Yeah.
Okay, thanks for the solution sharing, and thanks for our reporter Jing Kang for showing us the live view in Tel Aviv. Actually, I have a question from myself to you. Can you share your insights into the comparison between two-stage methods and one-stage methods towards the PSG task? And which one do you think will be the ultimate solution towards PSG?
Oh, that's a great question. So I can basically describe like the two-stage methods. They have a Panoptic segmentation result first, and then get relation based on the Panoptic segmentation result. So it's two stage, and one stage is like we directly get a relation, the object and the relation pairs directly from the image. So I would say the obvious advantage of a one-stage method is it can directly get information from image. So very straightforward. And yeah, so which I believe should be should improve our profit the long-term relation, which is difficult to catch. And yeah, and also I guess one stage is more like a vision, because you can catch directly from image. But two stage, usually we have so we have a mask first, already have the mask, and already have the mask features. So so collecting them to usually the usual practice is to fuse the object feature together and get the relation, which is which heavily depends on the further stage performance. And further stage performance, I'm not sure. So even though nowadays the very great Panoptic simulation methods, they have a very high score, like 50 something, but still not good enough, right? So we don't want the bottleneck is on the first stage. So maybe the one stage could be easier to improve. But the one stage is you can imagine the one stage so you complete the whole task in a one pipeline, and the computation cost could be big, the model could be bigger, and not easy to train or tuning. But and this is the drawback of the one stage. But and that's the impression of the two-stage, one-stage comparison. So what else is I also hope that two-stage methods, they can revive. I mean, so now the results shows that the two-stage is it still not, it does not exceed the one-stage methods, but maybe we can hybrid kind of. So we can have a good Panoptic simulation method first, and we can also add on some image information. And so in this way, the computational cost can be revised. And and also the overall information from the image can also kept. So I think two-stage can also work, and hopefully I can see some good solution from the participants. Yes.
Yeah, thank you so much. And I see it's getting dark on your in Tel Aviv. So enjoy your time at the ECCV conference.
Yeah, thank you. And Peter also said from the participants' perspective, two-stage are more stable and cost friendly. Yes. So yes, one stage you need many resources, not every laboratory can support.
Yeah. Okay. Thank you, Jinkang. Thank you for sharing with us about PSG today. And the audience, we can go and visit the PSG website to learn more about the data set and the challenge. Okay. Thank you, Jinkang. Thank you. Okay. It has almost come to the end of today's workshop. And finally, let's have Professor Ziwei Liu to give us the closing remarks. Ziwei, please take over.
Okay, so thank you, Ziqi. So I think all the the speakers and also the challenge participants has shared a lot of very valuable knowledge and insights about all the problems today. So the closing remarks, I very quickly go over 3 also the future trends. The first is kind of the boundary between hardware and software. So as you have noticed, a lot of current works, they rely on very new sensors and new setups to find new research problems. So that is definitely one way we should look for. That is that kind of the new hardware always brings new opportunities for the software and algorithm design. The second part is for the boundary between data collection and privacy. So as you see, modern models needs a lot of data to train, and the data itself always comes with the issue of privacy. So how can we balance like collecting enough data for the AI models as well as respect the privacy? So that is also we have to be very careful and considerable of. And the third is the boundary between synthesis and reality. As I see from the results of barley with stable diffusion, the current generative models have reached the point that is the quality of the results, like either in 2D or 3D, has reached kind of like human level. So at that level, can this generative model still help us understand more about like the artificial intelligence? So that is a very intriguing problem. Finally, I want to thank all the organizers, all the speakers, like for their time and efforts to make this workshop possible. And I think that's the end of this workshop, and hope to see you next year. Yeah, thank you again, guys.
Thank you.